Now, there it goes again. So let's look at this spreadsheet here, where we've filled out in more detail. This top part is what you saw of the type before. This is for a very coarse machine, a 5 millimeter accuracy machine. So this would be like a large crane. The actual numbers are basically irrelevant. What matters in this view I want you to see is these numbers here are based on errors that add up linearly. These errors are based on root square sum. So to get this 5,000 microns, where I'm saying the geometric and the load-induced errors are the only ones that matter, I'm not worried about thermal and process, they each got 2,500 microns. But based on root square sum, so the square root of 3535 squared plus 3535 squared equals 5,000. But you're never really that lucky that it's truly a random process. So this last one is, hey, I'm going to average the linear and the root square sum errors to give me an, quote, expected value of, if I make my machine with each of these two types of errors having allotted 3017 microns, they're never both going to take all of it. So my expected value will be the 5,000. That logic then I carry forward for the portion of error per axis, and then for each of the different types of error. Okay? So in other words, this 3017, for all the geometric errors, I have 3 axes. Well, 3 times 1400 is what? 4200. So you see what it really is, it's 3 axes, and the root square sum of the 3 axes is going to equal 3000. Excuse me, up here. And then there's the sum, and then the average of these two give me the expected value. This gives a little more realistic value what your hunting license will tell you you can do. So if you were to just do the sum of the errors, you would end up designing a very, very, very conservative machine. It would definitely work, but you'd probably be spending a lot more money. So you typically, by this method, the expected value of these individual errors is on the order of a factor of 2 from the sum errors, the errors. Okay? And again, this is an initial tool for letting you rapidly lay out what you want to design to. Once you've designed the concept from more than just the structural loop to putting in the details of the elements, then you can do finer and finer level of modeling and detailing. Ah! That was really fast. That's how fast errors can creep up on you. Ding! Out of nowhere. So I'm going to build a machine that's going to maybe be made of a bunch of these modular elements. And they really are nice. They're really perfect. But remember, everything, when it moves, has 6 degrees of freedom. That means, as this carriage is moving along, in reality, it's doing this. Wah! Woo! Or, yeah! And woo! Now, it's obviously not moving that much. But on the submicron level, that means fractions of a millionth of a meter it is. And if this has another piece of machine attached to it, down here a little bit of pitch motion can translate into a lot of linear motion up at the top. So our job is to figure out how to go from the catalog page to estimating what is a table that is held, for example, by the 4 of these linear motion guide carriages doing as it moves back and forth, and the linear guide carriages are doing their little wobbly thing. When you spec out a linear motion bearing, for example, or a rotary motion bearing, there will be a specification for how accurate that component is. For a linear motion bearing, what you'll get is called the parallelism error, which is a function of how long the rail is. What the parallelism error is how well this carriage surface moves with respect to a base that the bearing rail is attached to. These bearing rails are pretty good, but they're all dependent upon having a good flat surface to which you bolt them to really pull them down straight. And in fact, sometimes you'll take these out of the box and the rail is bowed. And you say, what? Well, when they make these bearings, they take these thin pieces of metal and they bolt them down to the table of a grinding machine. And then they precision grind them. And when you unbolt them, boink, they can pop. So they have to be bolted back down against a very flat surface. What matters is, with respect to predicting the error, is when the bearing is running, how well are the balls inside working? How well were these rails, the bearing races initially ground? All that will determine, as this carriage moves back and forth, how much up and down and side to side it's doing. That's called the running parallelism. If you really were to look with a laser interferometer, for example, as this thing is moving, what it's doing in addition to that, and you do the Fourier transform of it where you're plotting the amplitude as a function of wavelength, you'll see a plot somewhere around like this. And notice these numbers here. This peak here is occurring at like 0.1516 microns, millionths of a meter. And at different wavelengths. So the error, what may look like noise, actually is comprised of different wavelengths, just like sounds of an orchestra. And some of the error is coming from long wavelengths, which are as a result, as these bolts are tightened, if they're not tightened according to the specification the manufacturer gives you, they bend the rail. Or if you put this bearing rail down bolted to a granite surface with the same torque applied to the bolts as if you had bolted it down to a cast iron surface, you will also get a different wavelength according to the spacing of the bolts. The finer wavelength errors are created by the rolling elements on the inside rumbling around, sometimes touching each other, sometimes when they recirculate through the recirculating tube. All these things cause these little errors. They're reduced in bearings that are longer. They have more smaller elements. More elastic averaging takes place, will drive these low wavelength errors down. The wavelength errors on the order of the bolt spacing, you can drive those down by adjusting them. Either way, in the end, if you have a table that is supported at the corners by these bearings, we still have to figure out, in order for our error budget spreadsheet, to come up with, as the table moves, how much it pitches forward, rolls side to side, or yaws side to side. For rotary motion bearings, you have a similar thing in that as the bearing rotates, is it tilting? And how is it tilting? And is it moving side to side? Well, that's your radial error motion. And how can we estimate what that is? Now, you would never use just a single tapered roller bearing, but this was just to illustrate the effect we're talking about. There is a ANSI standard B89.3.4, which talks about the axis of rotation. Specifically, if you have a spindle axis, for example, this is a spindle axis on a machine, how, when it rotates, what is that axis doing? Is it moving, how's it moving up and down, in the radial motion, and how's it pitching, for example? All that can be similarly estimated by considering, if you have a spindle supported by bearings, as these bearings have their own radial error motions, this one's going up and that one's going down, that would cause some pitch in the spindle. You can get an idea of the radial error motion for a single bearing from the catalog, and by considering, for example, the spacing between the bearings, in the case of one going up, one going down, get an estimate for what the pitch of your spindle is going to be. That's the type of analysis that we'll be doing. You can take to the first order for rotary bearings, assume that the root square sum of the bore and the shaft roundness are representative of the radial accuracy of the supported shaft. And the rationale for that is when you buy a bearing of some particular accuracy class, you're not going to be pushing it into a bore that you chipped out with a hammer. So that'll be our first indication of what you can expect to get. That the bore has a certain roundness that you specified, and the shaft has a certain roundness you specified. And if the bore looks like this, and the shaft looks like that, which it will, based in extremes, as this rotates around in that, it's going to cause the bearing to deflect, and hence you're not really sure how this thing is wobbling up and down. That is why for rolling element bearings, we will make the assumption that the actual radial error motion that the shaft gets when supported by those bearings is this root square sum of the bore and shaft roundness as a worst case estimate for what that bearing is doing, or the supported shaft is doing. Then knowing those two values, that value of the rear and the front part of the spindle and the spacing between the two, you can then get an estimate for the tilt motion of the shaft delta 1 plus delta 2 over L, where this delta here at the bearing is equal to delta of the shaft, and if you want to find the delta of some point in front of the front bearing, what are you going to do? Well, remember, here's the center of stiffness. Which is where everything pivots about, and if this dimension here is A, so this delta of the shaft, or the spindle nose, is going to then equal to alpha times A. Which is the same thing, by the way, as delta plus this distance times alpha. Okay? So that's a very straightforward way of dealing with rotary motion bearings. Estimating for a rotary motion axis what the error motions are going to be. Now, remember, for rotary motion axis, as you're rotating around, there's pitch and there's yaw, which would be the same. You do not have roll, because that's the axis of motion. That's what you want to have happen. And then you have the vertical and the left to right radial, which are really the same component. The only item that's still missing is the axial motion, and that we will estimate by, if this is the axis of rotation, and here is the squareness of your bore, the seat in the bore for the bearing to press up against. For example, this is the bearing sitting in the bore, and here is one edge, the ideal position, and here is the other edge that it sits up against. There's a certain perpendicularity of this plane to which the bearing seats up against with respect to the axis of rotation, and that perpendicularity times the diameter of the bore, times the radius of the bore, will give us this error here, and that's what we will assume as this bearing is rotating, you're going to get that type of delta Z motion, or your axial error motion. Now how about linear bearings? We're going to do a similar way of trying to estimate what the error motion of a linear bearing supported carriage is in the following way. In both of these types of estimates, we're just going to consider what the bearing is doing. We're not going to worry about the bearing plus the structure. Or we're going to look at just what does the structural tolerance look like, and we're not going to worry about the bearing. The rationale being you're going to select a bearing or a tolerance in your structure to be commensurate with each other. You wouldn't pick a super precision bearing and then just bolt it down to a chunk of rough concrete. At least I hope not. So for the linear motion axis supported by 4 bearing blocks, we're going to assume the following. You have from the catalog a good idea, actually a quoted number for the running parallelism. So we're going to now assume that, let me get a prop here for my carriage. Bolt a plate here, and it's supported by, imagine there's 4, and this axis moves back and forth. I'm going to assume that the error motion in the vertical direction here, that's along the y-axis is shown there, is equal to the average of these 4 bearing blocks' vertical motion, which if they're all the same, it's going to be equal to any one of them's radial, or excuse me, running parallelism error. As this thing is moving back and forth, it's also going to go sideways, or my horizontal parallelism error is equal to, again, the running parallelism error of any one of these carriages. For the pitch, I'm going to assume as this goes back and forth, this carriage has gone down by the running parallelism error, and this bearing carriage has gone up by the running parallelism error, or boop. For roll, I'm going to assume that these 2 go down, and these 2 over here, imaginary ones, go up, and whoop. And for yaw, I'm going to assume these 2 front ones move that way, and these 2 rear ones move the other way, and boop. And that's what's shown here graphically in these images. Now I know what you're thinking. You're saying, yeah, wait a second, man. You just said that they're all going up for vertical parallelism. So if they're all going up, how can 2 go down in the front and the other 2 go back in the up for pitch? What did you switch? Well, for our machine, we're only looking at the running parallelism error. We didn't say we're looking yet, nor are we going to look at how good the surface is that the bearing rail is bolted to. There will be errors between those 2 also, but we're going to assume that this rail and this surface are good on the order of what these carriages are doing. So you see, that's where I'm doing this reasonable estimate as an engineer to pick from this running parallelism spec for any one of these blocks a fairly conservative estimate as that carriage moves back and forth what it's doing, pitch, yaw, and roll. And it works pretty well such that when we lay this out for an entire machine, we can ignore all the other types of errors, as I alluded to when we first started, because we're going to make it up in the fact that we're using this guesstimation of what the axis will do as it's supported by the bearing blocks. And it actually works quite well. You can write your own little spreadsheet for this, or as in a minute we're going to go into the error budget spreadsheet, you can have an added workbooks for each of the different axes where you do a diagram of where the bearings are located, the spacing between the bearings, what the running parallelism errors are, and then the spreadsheet using those basic spacings and running parallelism errors, you then calculate what the pitch, yaw, roll errors are, which feed into the main spreadsheet. So next stop, we're going to get into the error budget spreadsheets. All right, so if you're going to try to control your errors so they don't pop up unexpectedly, or if they do pop, they were manageable, See? We use error budget spreadsheets. What the spreadsheets do is they take your machine and they assume each axis can wiggle. So through your structural loop, you'll have many different axes. And we're going to look at each axis by itself. When this axis over behind it is wiggling, because of the error motions we just talked about a minute ago, it will carry this axis forward with it. But we will always just be looking at the tool, for example, what's the effect of this axis on the tool, this axis on the tool, this axis on the tool, including the Abbe errors that are happening. But we will always refer to those axes, errors at the tool, in terms of some reference axis. So we're always going back to a common frame of reference and figuring out what each of the machine components along the way contributes to the error motion of the tooltip with respect to a reference. That reference can be also just the workpiece. The reference is arbitrary. The simplest thing is always just assume it's at the workpiece. How is that done? Little math trick called the homogeneous transformation matrices. And the HTMs, as they're often just referred to, are a coordinate transformation matrix that says if I'm at one axis here, how do I move back to a preceding axis, including the effects of pitch, yaw, roll. If you have a multiple, like a spherical degree of a spherical joint, you're going to assume it's 3 rotary motion axes, one on top of each other with a common center point. For small angular motions, the order is not important. But if you have large motions, the order in which you rotate your axes will be important. You can run the experiment yourself if you say, I'm going to have 3 90-degree rotations. Do I go 90 degrees pitch, 90 degrees yaw, and 90 degrees roll? I end up with this. If I say 90 degrees yaw, 90 degrees roll, and 90 degrees pitch, what do I get? If I say 90 degrees of roll, 90 degrees of yaw, and 90 degrees of pitch, I get something very different. So the order of angular motions when they're large does matter. For little bits of wiggling, it doesn't really matter so much. These terms here, these are not zeros. These are the elements of the matrix. These are what are called the direction cosines, and these, the last row, is the linear offsets. So when I have this machine with what's called an open kinematic chain, the structural loop is like an open, like a C. It's very easy to just put an axis along the way. And that's what the HTM theory is. It's based on a linear chain. If I have a closed kinematic chain, for example, I'm designing a bridge type machine, and I want to so this would be my z-axis going up and down, and on my y-axis side to side, and then my x-axis driving along this way. How do I model this? And then here is the workpiece sitting in the middle. Where do I draw the structural loop? How do I draw the structural loop? Is the structural loop through here, or is the structural loop through there? Can't have two, or can I? Well, what you can do then in a conservative sense is you could try to write your own exact equations of motion. But what I'll do is I will go ahead and cut the machine, and I will pick the smaller half, because in general, if you think about it, you've got a smaller half of the machine which can open and close, and it's somewhat supported by the larger part of the structural loop. And then when I go to estimate this axis, when this axis moves, what happens to the spacing of the bearings with respect to the yaw pitch roll we just talked about, I'll go ahead and use a very large spacing such that when this axis moves, the roll motion is very, very, very small. For some machines, like you can imagine there's a linkage, you can actually write the closed form equations, but that's not then using this spreadsheet model. You'd be doing your own exact model, which is fine. Your goal, remember, at this stage is how do you move fast to predict the potential for the design you're envisioning to meet the specifications of the machine. So in this spreadsheet, which I will bring up in a minute, spreadsheets have workbooks, and I'll go through the different pieces of the spreadsheet here in a second. And there's different axes we enter in. And I will often have the sketch of the machine I drag around for reference when I'm working on the modeling the errors in each of these sheets. And the most important thing when you're using this spreadsheet is don't go adding and deleting rows in the master. You're able to, in any of the subsequent workbooks, do whatever you want. But be very careful about any of the spreadsheets when you add or delete rows. Always keep a control copies fresh and minty clean somewhere that if you mess up, you can always reload it. The net result of the spreadsheet in the end is it's going to tell you what it believes is the sum of the random errors in the reference coordinate system between the tool and the workpiece, what is the root square sum of the random errors, and then what is the average of those sum and root square sum errors. It's also going to tell you then what it believes the net total systematic errors are. We'll see in a minute on the spreadsheet you can enter in different types of errors. Random errors where you don't know the sign, and systematic errors where they definitely have a direction. For example, because you know the machine is long and it's got a weight in the middle and it's going to have some sag in the middle as you go. But for most part, when you're starting at these early phases on looking at the machines, you're just going to be starting dealing with random errors. So we'll go back and resurface in a minute with the spreadsheet, which we'll walk through in a little bit more detail. Remember, all the spreadsheets we've been talking about, later on there'll be subsequent lectures where I'm using the program where I can talk about the spreadsheet as I click through it, but you won't see my smiling face.